Hello everyone. In this video, we are going to talk about inductors. Inductors, similar to capacitors and resistors, are passive elements, okay? So they react to the changes in current of the circuit. They don't need an extra source of power. And they are typically basically wires that are wound around some basically metal or magnetic, what we call permeable cores. So you can create magnetic fields inside and around them. So the basic property of them is if you try to change the current going through these wires, they resist that. They don't like you to change the current. So they are like inertia elements in electric circuits. They act similar to inertia. They don't like you to change the current. If you do, they create a voltage, and that voltage is going to be opposite to the voltage that caused that change in the current. So they try to oppose that. Okay. And since the current going through them creates a magnetic field, so they also act as storage units. But the storage is through the magnetic field as opposed to capacitors that stored it in terms of electric fields. These are storing it with magnetic fields. And they have the unit for that called inductance, and it's measured in Henry, and we're going to see that. Okay, so mostly you're going to see these wires wound around some core. That is your inductor. So let's learn more about what inductor does. So first thing is, as I said, when the current goes through an inductor, the wires of inductor, you will get a magnetic field. Now, how big is this magnetic field? Which direction is the magnetic field? First let's discuss that. So here is this solenoid, these wires in brown that are wound around this cylindrical metal or core. And the wire is going in the direction that you see. It goes in like that, comes out like that. So the wire on the current on these wires is flowing like this. So which direction is the north and south of that magnetic pole? Here you use your right hand rules. If you use the fingers of your right hand and bend the fingers of the right hand in the direction of the current, so these are the four fingers of the right hand, you bend them in the direction of the current. If you do that, then your thumb of the right hand will show the direction of the north, as you can see here, right? So the north is the direction of the thumb of the right hand. So this is, we call the right hand rule. And of course, the other side is the south. So that's about the direction of this magnetic field. Now, if you look at it, inside the core, the flow, the magnetic flux, we call it, these lines are called magnetic flux. The magnetic flux, if you look at it, inside the core is from south to north, and outside is from north to south. Okay, so if you look at the direction of these arrows, you see outside it is from north to south, these curves, but inside, if you look, it is from south to north. Okay, so these are the directions of magnetic flux, we call it phi. We'll see that. This phi, or magnetic flux, is what you have. That is the amount of magnetic field that is going through some area. So it's BA, or integral of B dot dA. So the magnetic field B times the area it is passing through, that is called the magnetic flux. So this is for the direction of it. Now, how much is the magnitude of it? In order to find the magnitude of it, we can use what we call the Ampere's law. So the Ampere's law says that if you have some element that contains your current, and the length of it is L, integral of BdL over the entire length of the surface is mu times I. What does that mean? Means if you have a wire like that, okay, and the current passing through it is I. Around this current I, around this wire with current I, there will be a magnetic field, which again comes from the right-hand rule. So it is going to be like this, that B. So it says if you consider like a cylinder around this, consider a cylinder where this magnetic flux goes in and out, integral of B dot dl, and dl is a short length of elements along the length of this wire, that is equal to mu times I. What is I? I is the current going through it, L is the length along it, and mu is what we call basically the permeability, which I just mentioned earlier. That's the permeability of the material. Now, if you wind these wires around some core material, mu is going to be mu of that material. If it's just some coil that is wound in the air and nothing in between them, then that mu is called mu naught, which is for the air. But if there is a metal, a magnetic core in between, then it is mu r times mu, where mu is the total permeability of that core material, whether it's iron or anything else. Okay? So for the case of this scenario here, single wire, of course, B dot dl can be replaced by BL, because B is uniform along all L, so you can just do it as BL, and mu times I. Okay? Now, if you have more than one wire, if you have N wires going on, then it is going to be N mu L, because you have N of those I's that are inside that control volume. So BL is mu Ni. If you solve for B, B is going to be N mu I over L. So that is the magnetic field. Okay? So you see, it depends on how many wires you have in here, and I have to change that N to capital N because I'm using two separate notations here. So let's use all capital N's. Your formula is going to be B equals mu Ni over L. Well, this L here is the total length of the wire. Okay, this small L that you see, that's the total length of the wire. And assuming that you have N wires inside that control volume, okay? Which happens when you do have a basically coil, right? So when you have a coil, there are going to be N of these wires in some specific length. So this N over L, if you would, this N over L is this one, this parameter here, N over L. That's the number of wires per length. Some books use small n for that. So you see, they say B equals N times mu times I. Or they say N mu naught times I, where assume that there is no magnetic core, so the wires are just wound around nothing. There is air between them. So depending on that's mu naught or mu, depends if there is a permeable magnetic core or not, and whether you use a small n or instead of a small n, you use capital N over the total length. That is basically the magnetic field inside an inductor. Okay, so that's about that. Now, let's talk about the part that what happens when you change the current inside an inductor. What happens? As I said, it opposes that. It resists change in the current. And that will cause it to create a voltage inside it. Okay? And the voltage, the direction of the voltage is determined by the Lenz's law. And this opposition to the current is what we call inductive reactance. So let me tell you what happens. What is inductive reactance? What is the Lenz's law? What happens when you try to change the current now? So far, we learned about the fact that if you pass a current, you get a magnetic field. and this is the one that stores energy and everything. Now the main capability of inductor is resisting the change in the current, inductive reactance. Let's explain that right now. So here we consider two separate scenarios. You have an inductor in the circuit, right? This winding. And you have this voltage. There is a resistor, and the resistor's resistance here can change. Why do you put a variable resistor there? Because you want to change the current, right? So if you make the resistance bigger, the current is going to go down. If you make it smaller, the current is going to go up. Okay? So here we are going to look at those scenarios here. So scenario one, you brought down the resistance and the current is increasing. Okay, so I is going up in the circuit. What happens? If you have a voltmeter and measure the voltage across this inductor here, you see that when the I was constant, as long as I was the same value, this voltage, if you call it V sub L, that V sub L was 0 as long as the current was not changing. But as soon as the current is changing now, you see that this VL is going to go up. And you see that here, this dial is moving from the center, it is moving to the right side, right? You see here, this dial is going to the right, your voltage is increasing. Now, how much is this voltage VL? And in which direction is that? Because right now you can see that the direction of this voltage is in the opposite direction of your circuit. Your circuit wants to send the current in this way, that's positive, negative, but if you look at your inductor, you see the positive of that is in the opposite direction of this, okay? So what is it? So let's talk about that. So first, how much is the voltage? The voltage of an inductor is determined by this formula, L di over dt, where di over dt is the rate of change of current, and L here is a constant, which we call inductance of the inductor, L. And for an inductor, this inductance is given by, as you can see, mu n squared A over L, where L here is the length of that coil, n is the number of turns, the same n that we had above, mu is the permeability of the core, A is the cross section of the coil, and L, capital L, is that inductance that, as I said, you are measuring it in henries. Okay? So we have two L's here. Pay attention. This capital L is inductance. This small l is the length. And if you look at L here, the formula for L and the formula for magnetic field, you see there are similarities between them, right? Look, they both have mu in them. B has one power n. This has two power n's. They both have L in the denominator. This one has one extra A. So if you compare B and L, you see that, and B has I, L doesn't. So if you want to relate the magnetic field of the inductor to its inductance, all you need to do is to use the second formula, that B equals I over NaL, right? So L is the inductance of the inductor, I is the current going through it, A is the cross section of these circles, right? So this cross section here, that is your A, and N is the number of coils. So you can relate B to L as well if you want through this top formula here. And that is your inductance formula. The units for measuring that is called henries. Okay, good. So V is proportional to rate of change of current, as you can see. So when current is increasing, this L is always a positive number. When I is increasing, di over dt is positive. So L di over dt is positive, so VL is positive. And you can see that here it is in this positive direction from this side to this side. Now, what happens when it is like that? When it is like that and in this positive direction, the value of it is increasing, what happens? Well, it is opposing, because these positives are against each other, it is opposing this voltage. Basically, it creates a voltage drop here for you. And when it creates a voltage drop, so the voltage across this resistor here is going to be what? It's going to be V of the supply minus V of the inductor, correct? So in this case, Vs equals VL plus R times I. And when this VL is positive, what happens? The total voltage available across the resistor is going to be Vs minus VL. So you see your total voltage, effective voltage across the resistor is dropping by VL. So when you divide it by R and calculate I, you see what's going to happen. Because this VL is positive and it's going up, especially the faster the I is changing, it causes the current to go down. So you see, current was initially going up because I changed the resistor, but now this inductor's voltage is causing it to go down. It is opposing that increase. Say, hey, why did you increase it? I didn't like you to increase it. Now I'm trying to increase my voltage to bring the current down and put it back to whatever it was. I don't like that you changed it. And the exact opposite happens when you're decreasing it. Here, you're decreasing it, so di over dt is negative. When it's negative, this voltage across the inductor is going to go the other direction. Look, you see, it's to the left side instead of to the right. So in this case, you will get Vs plus VL equals Ri. And so what happens, because you're adding something to the source voltage, your total effective voltage is going to go up, and so that means the current is going to go up. So you try to bring it down, but the inductor is trying to force it back up again to go back to whatever it was. So the voltage created across the inductor is always opposing the change in the current, as we said. And the fact that it is in this opposite direction, that is what we call the Lenz's law. And this property, we call it inductive what? Reactance. Okay, so we learned how the inductor does it and what is the relation between voltage and the current for it, VL. Now, this is V versus I. If you want I versus V, then you need to multiply both sides by T, divide by L, and integrate. So the current through the inductor is 1 over L integral of what? Integral of voltage. Okay, so that's the voltage current or current voltage relation that you can see right here. Good. Now, if you want to compare this against a mechanical system, you can say it is similar to a fluid system, and there is this pump that wants to create flow inside it, and your inductor basically is similar to this wheel here, this paddle wheel or turbine or whatever you might call it. And the resistance of that to the flow can be considered like what? Like the inductor. So what's happening here? Initially, when this pump starts spinning, it is sending the flow to the wheel. Wheel is stationary in the beginning. It doesn't want to be spun. Okay, so it resists the flow. And so it creates basically some opposite force in the direction of the flow to slow it down. Good? So initially, it doesn't like the flow to go from zero to non-zero, because your flow here is similar to the electric current, because electric current is flow of electrons. So because flow here, m dot, is going up, that is similar to the I is going up. So the change of that mass density, the flow rate, is something this paddle wheel doesn't like. It tries to resist it. So it resists a little bit, but if pump is stronger than this, pump will ultimately force this guy to spin as well. And when this mass flow rate is increased to some steady value, then this m dot is going to go to some constant value. And since it's not changing anymore, then the resistance of this basically wheel is going to stop. And without too much resistance, this guy is going to spin just like anything else in the circuit. Okay, so resistance happens as long as your flow is changing. If your flow stops changing, the resistance goes away. In this case, the resistance of this is similar to the voltage for the inductor. Now, the next thing we're going to talk about is the impedance and the reactance. Okay, so the impedance is defined as the voltage of the element divided by the current of the element. And remember, impedance is the imaginary, or reactance. Reactance is the imaginary resistance. If you add it to the actual resistance, the whole thing is called impedance. So impedance is voltage over current. Now, in this case, remember your L is, your V is L di over dt. So if you apply Laplace transform, you're going to get V of S equals L times S times I of S. And if you find V over I, clearly it's going to be L times S. And if for S you replace j omega, then it is going to be what? It is going to be L times j omega. And if for omega you replace in frequency in hertz, it's going to be L j 2 pi f. Okay, so basically your impedance is going to be L j omega. And if somebody says, what is the reactance? Because remember, reactance is only the same as for an inductor, which is only imaginary resistance, is the same. So if I want X of L, right, it is simply L times S. That's the same thing, but this S is going to be replaced with omega only, no J. So XL omega is going to be L omega. Okay, it acts like a derivative element, basically, in your circuits. So that is the impedance, or in this case, the reactance of your inductor. Now, how can you use this? So you found it. Now, what's the application of it? Let me show you the application. So let's say one of the common things that you have is what we call a second order circuit, or RLC circuit. So many times you have RLC circuit. So you have your voltage here, this V in. And this V in could be variable, okay? And then you have your resistor, then you have your inductor, and you have your capacitor. Okay, so this is L, this is R, this is C, the current is called I, and this V in could be variable, okay? So it is a variable voltage. And your output could be anything. So if I want to just find the current, so you can get your output from C, R, or L. If I want to find the differential equation governing this circuit, what do I do? If I use the Kirchhoff's voltage law, and that is V in minus the voltage drop across the resistor, which is Ri, minus the voltage drop across the inductor, okay? Now here it's going to be L di over dt, and for C it is going to be basically 1 over C integral of I dt, right? So if I want to do it in differential equations, it is going to be like this. And clearly it is a differential equation, but you don't want to have the integral, so you have to take time derivative from both sides to get it into a second order differential equation, and you can do that. Now, another way you can do it is to replace this inductor and capacitor by their reactance term. So this guy, assume, is an imaginary resistance for which the resistance is L times S, and this guy is also an imaginary resistance that the reactance of it is 1 over CS. If that's the case, And let's say in this case, you want your output to come from what? Let's say you wanted to get it from the capacitor. So this is your V out. And let's say you want to find a transfer function or anything. So in this case, this is what you do. You say that the voltage drop across the inductor is its reactance, Ls, times its current, I. And for capacitor, it is its reactance 1 over Cs times I. This is equal to 0. And then the output here, V out, is simply equal to 1 over Cs times I. That's all you need to do. If you look here now, clearly you have two equations. And if you eliminate I between these two equations, which is all you need to do, you can easily find the transfer function of the system. So you can see that V out in this case over V in is what? It is going to be 1 over Cs divided by R plus Ls plus 1 over Cs. And if you continue and simplify, you are going to get LCS squared plus RCS plus 1 and 1. And you can clearly see that your system is a second order system, right? So if you want to find the natural frequency of that, if you want to find the damping of that, damping ratio or something, you clearly can do that, right? So in this case, your omega n squared is going to be 1 over LC, and then 2 zeta omega n is going to be RC over LC, which is R over L. So from here, you can find the natural frequency, the damping ratio, and the damp frequency and everything. And you can plot the frequency response of the system. Okay, regarding inductors in series and parallel, we have to know that inductors are similar to resistors. So in series, the equivalent is sum of them, and in parallel, reciprocal of the total is sum of the reciprocals, okay? So they act similar to resistors, and it is quite a bit clear why, because here, if I connect them to a voltage source, right, any voltage source, and let's use general V in, and then there is I that goes through them, you know that I1 and I2 in this case is going to be the same. So I equals I1 equals I2 because it's a series connection. But V, the total V here, V in, that is equal to basically sum of the two drops. So it is equal to V1 plus V2. And we know that V1 is L1 dI1 over dt. And the second one is L2 dI2 over dt. Now, if I replace it with an equivalent, I and V in this case, this V in is simply going to be the L series, the L equivalent, di over dt. Okay? And remember that the i's are the same. Since i's are the same, their derivatives are also the same. Okay? So this di over dt and di1 and di2 over dt, they are all the same. And clearly you see that ls is going to be L1 plus L2. Very obvious. Okay, that's for the series case. For the parallel case here, then again, if you call this V in, here the V's are equal. V of the both ends of L1, L2, and the total V are the same. So V in here equals V1 equals V2. And if you compare it against the equivalent circle, so here your V in is equal to L of parallel di over dt, and that is your basically Vn. This V1 is similarly L1 di1 over dt. This is L2 di2 over dt. And the thing is, the I that goes in this case, is sum of I1 and I2. So I here, if I want to write it, I write it as L d over dt of what? I1 plus I2. So it is going to be LP di1 over dt plus LP di2 over dt. Okay, that is your V in terms of these, right? And then, based on what I have up here, this is equal to L1 di1 over dt, and this is equal to L2 di2 over dt. Okay, so if you look at this here, right, clearly the only solution for this is this guy here. If you want these equalities to all hold, what we need to replace LP with is, if you simplify this, it is going to be L1 L2 over L1 plus L2. So if I replace that over here, okay, you can get the result. Because if you look at these last two equalities, from here you can see that di2 over dt is equal to L1 over L2 di1 over dt, right? So you can bring this result and plug it right here. Okay, if you do so, what would you get? You get LP times di1 over dt plus L1 over L2 di1 over dt, which is this side, is equal to L1 di1 over dt. Now both sides have di1 over dt, so you can cancel it out. And from here, you see that LP times 1 plus L1 over L2 should be equal to L1. Multiply both sides by L2 and take a common denominator, and you'll see that LP should be L1 L2 over L1 plus L2. Or you can say that 1 over LP is equal to 1 over L1 plus 1 over L2, and if there are more, you can add them as well. So you see that they are acting exactly like resistors. In parallel, the total inductance LP is less than all the individual ones, and in series it is more than all of the individual ones. Okay, so their behavior is exactly like resistors, the formulas that you have for them. Okay, then we go to inductor types. What type of inductors we have? So here I came up with 6 different ones for you. So some of them are, we call air core conductors. These are the one that there is no magnetic core, so that mu that we use in their formula, that mu should be mu naught. Okay, remember here that we had some mu, right? This mu is for a metal. If it's just air, the only thing we have is what? Is just mu naught, or inductance. When you look at this formula, this mu should be mu naught. If you look at their magnetic field, there should also be B equal mu naught Ni over L. And the number for it is 4 pi 10 to the negative 7 henries per meter. Okay, so this is for the ones that have air inside them, nothing inside. These are good for high frequency circuits and radio transmissions. Then the ones that have an iron inside them, so clearly their mu's is not mu naught, is bigger than mu naught, so they have increased inductance. You can use them in transformers and power supplies. They're the one that have a ferrite material in general in them, and so they can use them in signal filtering and RC circuits. They are the one that are around the torus or a donut shape. Okay, again, they are used in high frequency power circuits. There are the ones that called choke inductor. So these basically are used for filter and noise suppression. Now, the reason they are blocking high frequencies is because if you remember, the reactance of an inductor is L times omega. So the reactance is increasing with frequency. So when the frequency of signal goes up, the reactance goes up. So it tends to block higher frequency signals, okay? And then we have the ones that are variable. So their inductance can change, okay, their values, because you can change the number of the number of basically wires in the length. And it's not just by frequency, so you use them in oscillators or circuits that are tunable. So you can change their L values. As I said, if you go back and look at here in this formula, the real variable parameter here is N, because mu is constant, that depends on the core. A, you have to squeeze this shape around the core, which is not possible, and N and L. So what you can change is N over L or just N or L. And most of the time it's the N over L that you are changing. Okay, so you can make a variable inductor. And regarding their applications, as I mentioned, you can use them in power circuits to smoothen out voltage fluctuations because they act like inertia. Okay, L's are acting like inertia. In mass spring damper systems, they are similar to a mass. They are inertia. They make the system heavy, so you cannot easily change the current in it. They resist current changes. And of course, the voltage changes as a result of that. And of course, because they have inertia, so they can transfer energy between the circuits because of that. They store energy in terms of magnetic field. You use them in radio frequency communication devices, in RF circuits. As I said, they store energy. You can use them in sensors that are inductive and proximity sensors. So there are some sensors that their L, as I said, can change. Okay. And we'll talk about the proximity sensors and so on. There are capacitive ones, inductive ones, and so on, where the capacitance or inductance changes when the object gets closer to them or further away, and that causes a change in voltage, and that can be measured and give you an estimate of the distance or whether object is close or not. And in tuned circuits like oscillators and frequency selective networks, they are used. So each one of these, if you want to get into them, needs a lecture of its own. So that's not my goal here to go through each and every one of them. Just want to give you a rundown of some applications. And if you want, we can go over each one of them, although I don't want to get too much into them. I want to just talk about here mostly the applications and the basics of inductors. So hopefully this video was useful to you, and I'm going to see you in the next lecture. Thank you.